For the last spotlight of this group of spotlights, we have Ilya Bugonovich presenting about adversarially robust optimization with Gaussian processes.
Hello, everyone. This is a joint work with Jonathan Scarlett, Stephanie Gelka, and Volkan Jevher. In this talk, we look at the black box function optimization problem, where our goal is to optimize some unknown utility function f. No gradient information is available, and the only way we can learn about this function is through noisy and expensive point evaluations that are chosen sequentially. We focus on a popular approach to this problem known as Bayesian optimization, which models the unknown function as a Gaussian process and allows us to encode the smoothness properties by suitably choosing the kernel function. This approach has proved to be very effective in practice, particularly in reducing the number of expensive function evaluations. In our paper, we look at the robust version of the previously explained problem. Our goal is to discover a design X star that maximizes the unknown function, but that is also robust with respect to the worst possible perturbation that we denote with delta. So in this setting, the final reported point by the algorithm might be perturbed by an adversary up to some maximal distance that we denote with epsilon. So the main motivation for studying this problem is that we seek to discover a design that is robust with respect to possible adversarial attacks, implementation errors, or any other source of perturbation. In this image, we illustrate the main difference between the robust and the non-robust problem. We show the original function that we sequentially query, and we also show the version of this function that is perturbed function version for some particular value of epsilon. So in this example, the design that corresponds to the global maximum of the original function is non-robust with respect to adversarial perturbation and is strictly suboptimal for our problem. On the other hand, a design that corresponds to the local wider maximum of the original function is both robust and the optimal solution to our problem. A great number of non-robust Bayesian optimization methods have been developed over time. We list some of them on this slide. In our paper, we developed a robust Bayesian optimization algorithm that we call StableOpt. We were inspired by the Gaussian process upper confidence bound that works in the non-robust setting. So at every round T, StableOpt computes model-based upper confidence bound of the unknown function, and then in the first step, it selects a point that is maximum optimal in terms of this score. In the second step, StableOpt tries to estimate the robustness of the previously picked point by looking at the worst possible perturbation for this point. Here we are being pessimistic in the face of uncertainty, meaning that we're using the lower confidence bound in order to find the worst possible perturbation. In the final step, StableOpt just observes the noisy function value at the perturbed point, updates the statistical model, and then this procedure repeats in rounds. Our main theorem states that if you use StableOpt to sequentially query the unknown function sufficiently many times, then we can report a point x capital T such that the perturbed function value of this point is at least the optimal perturbed value minus some target accuracy that we denote with eta. We can observe that the total number of points that we need to query, denoted with capital T, depends on the target accuracy that we want to achieve, but it also depends on the kernel-dependent information quantity, denoted by gamma. So this theorem works for general kernels, but in our paper, we also provide the kernel-specific bounds. So StableOpt and its theory can be easily extended to various different robust optimization settings. For example, robustness to unknown parameters. Here, the goal is to choose parameter x that is robust with respect to different possible values that some other parameter theta can take. For example, when tuning hyperparameters, we might want to find hyperparameters that are robust with respect to different data types. One more interesting setting is the one of robust group identification. Here we assume that the input space is partitioned into groups, and our goal is to identify the group with the highest worst-case function value. For example, in group movie recommendation, we would like to recommend a group of movies to a particular user such that every movie from within this group is up to the liking of the user. As I already mentioned, StableOpt and its theory easily extend to these and some other interesting robust optimization settings. So for more information on StableOpt and its variations, please come and visit our poster. Thank you.